Hello, in this lesson we'll continue with Taylor series. In the last lesson we did the motivation. This time we're actually going to derive the series itself. It gets kind of complicated with all those integral signs flying around everywhere. Don't be disheartened by it. If you lose your place, pause the video and go back a bit, and don't be afraid to watch it multiple times. I think it's a pretty complicated thing. Confused the heck out of me the first million times I saw it. Now that I've seen it a million and one times, I think I'm starting to get the hang of it. Anyway, enough rambling. Let's go to it. So first, I want to recall the fundamental theorem of calculus. Well, not the whole theorem. I just want to recall the fact that the fundamental theorem of calculus tells us that if a function y of x is differentiable at the point x equals a, then we have y of x minus y of a is equal to the integral from a to x of the function y prime, and we just need some dummy variable there. T1 is as good as any. So y prime of T1 dt1. Fundamental theorem of calculus tells us that. And therefore, by adding y of a to both sides, we have that y of x is equal to y of a plus the integral from a to x of y prime of T1 dt1. Okay, so nothing hugely controversial there, as long as you know the fundamental theorem of calculus and you're fine with that. Well, what we did here works for any function y that's differentiable at the point A. Now, suppose that y can be differentiated again at the point A. Well, that means that y prime of T1 can be differentiated again at the point A. Well, if that's the case, we can do exactly the same thing again with y prime of T1 this time. So by the same theorem, we have that y prime of T1, assuming that y prime of T1 can be differentiated at the point A. So assuming that, we have y prime of T1 is equal to y prime of A plus the integral from a to T1 of y prime prime of some other dummy variable, let's call it T2, dt2. Okay, so again, nothing hugely controversial. We took this thing and we applied exactly what we did to the function y of x. We applied it to y prime of T1, and so we get that. And now all we need to do is take this thing and stuff it into this part, because they are exactly the same. So because the thing in the box is equal to this thing that I just underlined, we can just go ahead and substitute everything in. So let's do that. Oh, okay. So dt2. All right, so I'll use a different color. Substituting in the red part into the underlined in red part, we have y of x is equal to y of a plus the integral from a to x of, and I'll use some curly brackets here, I better write it in red again, y prime of a plus the integral from a to T1 of y prime prime of T2 dt2. And don't forget, we're still taking this part dt1. That's still being integrated with respect to the variable T1. All right. Let me write that out again at the top of the next page to give some room. So what we have is y of x is equal to y of a plus the integral from a to x of y prime of a plus the integral from a to T1 y prime prime of T2 dt2 dt1, the whole thing dt1. So the whole thing in the curly brackets integrated with respect to T1. Well, because integration is linear, we can expand this out. So y of x is equal to y of a Plus, now, here's an important, maybe subtle detail to recognize. This y prime of a actually doesn't have anything to do with t1. Now remember, when we expand that out, we're going to be taking it, we're going to be integrating over the variable t1. Well, y prime of a is just a number. It doesn't depend on t1 at all. So actually, what we can do is bring it outside the integral sign. So plus y prime of a times the integral from a to x dt1. Now, the other part, so this part here, plus the integral from a to x of the integral from a to t1 of y prime prime of t2 dt2 dt1. Okay, so again, you can follow backwards if you got a little stuck there. I don't blame you. I still think it's confusing, but it all works. You can prove that it all works. And so now, what we're going to do is actually we're going to do the same thing one more time, just for the sake of completeness, and we're going to do everything to y prime prime of t2, assuming it can be differentiated again at the point A. So assuming y prime prime of t2 can be differentiated at the point A by exactly the same logic as before, we have y prime prime of t2 is equal to y prime prime of a plus the integral from a to t2 of y prime 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 of t3. And so now what we do is we do our substitution. We go ahead and we put what we just worked it out to be into here in place of the y prime prime of t2. So curly brackets go in place of the y prime prime of t2, and let me write out what we get. What we get then is y of x is equal to y of a plus y prime of a times the integral from a to x dt1 plus the integral from a to x, integral from a to t1, and then our curly brackets, y prime prime of a plus the integral from a to t2 of y prime 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 of t3. And this is integrated with respect to t3. Close up our brackets, and we're integrating the whole thing in the brackets, first with respect to t1, and then we integrate it again with respect to t2. Running out of room. I hope you can read that last part. If you can't, it's dt2. Okay, and so now, once again, because our integration is linear, we can expand it over this factor and then this factor. And so by doing that, we get y of x is equal to y of a plus y prime of a, I'm just writing out the first line again, times the integral from a to x dt1 plus, now again, this y prime prime of a, this y prime prime of a doesn't depend on either t1 or t2. So we can just bring that out the front of the integral signs. It doesn't change anything. So this is y prime prime of a times the integral from a to x, integral from a to t1, dt1, d2, dt1, dt2. So integrating first with respect to the variable. Did I get that the right way around? Oops, I mixed up here. This should be a dt2, dt1. So dt2, dt1, and dt2, t1. Sorry about that. Hope that doesn't make things unreasonably confusing. So remember, it goes in decreasing order after the integral signs, d2, d1. All right. So we're nearly done. And that means we're integrating first with respect to the variable t2 and then with respect to the variable t1. Okay, so finally, plus, now we expand over this part here. We take these two integral signs and this part. And what do we get? We get the integral from a to x, the integral from a to t1, hope I don't run out of room, integral from a to t2 of y prime 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 of t3 dt3 dt2 dt1. Okay, and as you may have guessed, we could, if we wanted to, we're not going to because I'm sick of writing these out already, we could, if we wanted to, do the same thing to y prime 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 of t3, assuming it can be differentiated at the point x equals a. Okay, so in general, assuming that a function y of x can be differentiated n plus 1 times at a point, then we have that the integral from a to x times the integral from a to t1, or not times, the integral from a to x of the integral from a to t1 of dot 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 of the integral from a to tn minus 1 of the function y differentiated n times at the point tn dtn, so integrated with respect to tn dot 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 all the way to integrated with respect to t2 integrated with respect to t1. So this tn goes with this integral, this t2 goes with this integral, and this t1 goes with this integral. Well, what we can do is basically just do the same step that we always do. We know that this has got to be equal to, if we write y differentiated n times at tn, if we again use the fundamental theorem of calculus, then we know that this is equal to y differentiated n times at the point a plus the integral from a to tn of the function y differentiated n plus 1 times with this, and I see I made a mistake in the notes here, y differentiated n plus 1 times of the variable t n plus 1 dtn plus 1. So if we go and substitute that and then expand, what we get is y differentiated n times at the point a multiplied by all those integrals, a to x, integral from a to t1, all the way up to integral from a to tn minus 1, and then with respect to tn, with respect to t2, with respect to t1, plus the integral from a to x, the integral from a to t1, all the way up to the integral from a to tn minus 1, times the integral from a, or of the integral from a to tn of y differentiated n plus 1 times at the point tn plus 1, of the dummy variable tn plus 1, it's differentiated n plus 1 times at the point x equals a. And then that's dtn plus 1 all the way up to dt1. So, in general, we can do this step. We can take that thing on the end of our big long equation that's getting longer and longer each time we do it, and we can make it longer still. We can split it up into another two parts with the second part, again, one integral longer. So, if we keep doing that, well, as long as we want, we can write the function y of x as the following. Y of x is equal to y of a plus y prime of a times the integral from a to x dt1 plus y prime prime of a times the integral from a to x integral from a to t1 dt1 no dt2 dt1 plus, and we can keep going, and we get up to all the way y differentiated n times at the point a times the integral from a to x times the integral from a to t1 all the way from a to tn minus 1 dtn dt2 dt1, and then our last term is of course the integral from a to tn, integral from a to x, integral from a to t1 all the way to the integral from a to tn minus 1, and then the integral from a to tn of y differentiated n plus 1 times at the point a, y differentiated n plus 1 times, and then we put a dummy variable in. So y differentiated n plus 1 times of tn plus 1, and then dtn plus 1 all the way down to dt1. So in general, assuming the function can be differentiated n plus 1 times at the point A for some x in the interval that it can be differentiated n plus 1 times on, we get this big, long, horrible looking thing. Well, we can actually make it look slightly better. We can make it look a bit better than that by noting the following. I'll do it down here. By noting the following. The integral from a to x dt1. Well, that's actually nice and easy. It's just the integral from a to x of the function 1 dt1, which doesn't really depend on 1 at all. So it's going to be, well, it's just t1. And t1 is evaluated at x, well, t1 equals x to t1 equals a. And when we put that in as normal, we get x minus a, because we replace t1 by x, and then we replace it by a. Remember, t1 is the variable of interest here. So we replace it by x, and then we replace it by a, and then we subtract, as per usual. So this is just equal to x minus a. Okay, let me do another one then. On a similar note, we have the integral from a to x of the integral from a to t1 dt2 dt1. Well, if I integrate that twice, I'm going to get the integral from a, if I integrate it once first, I'm going to get the integral from a to x of t1 minus a dt1. Okay, well, I can basically, there's a couple of ways I can do this, but I can actually just treat t1 minus a as a single variable, because if you think about the chain rule, t1 is not being multiplied by anything. So if I integrated t1 by itself, I would get t1 squared divided by 2. But subtracting a doesn't actually make a difference. Subtracting a doesn't make a difference because the t1 is still not being multiplied by anything. So by reverse chain rule, this is actually going to be equal to t1 minus a squared divided by 2, and this is going to be evaluated at t1 equals x and t1 equals a. Well, if we go ahead and substitute that in, we're just going to get x minus a squared divided by 2 minus a squared. Well, a minus a squared is just 0, so we don't even need to worry about the other part. So that works out to that. And I'll leave it to you to convince yourself that the integral from a to x, the integral from a to t1, the integral from a to t2, if we just keep integrating, dt3, dt2, dt1, I'll leave it to you to convince yourself that this is actually just equal to x minus a cubed divided by 3 times 2 times 1. And this is equal to x minus a cubed divided by 3 factorial. And finally, we can say that in general, the integral from a to x, the integral from a to t1, dot, 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 the integral from a to tn minus 1, dtn, all the way up to d2, dt1, this is going to actually be equal to x minus a to the power of n divided by n factorial. And so remember that big, long, complicated formula we had with all, these nasty integrals in them? Well, I'll go back to and have another look at that formula. And what we can do is actually replace all these terms with these nicer looking ones. So we end up with the following. We end up with this. We end up with y of x is equal to y of a plus y prime of a times x minus a plus y prime prime of a times x minus a squared over 2 plus, and we keep doing this all the way up to y differentiated n times at the point a times x minus a to the power of n divided by n factorial plus, and then we still have this big, long, horrible integral, the integral from a to x, integral from a to t1, all the way up to the integral from a to tn, y differentiated n plus 1 times of the variable tn plus 1, dtn plus 1, all the way down to dt2, dt1. So we still have that part, and I'm circa writing that part out. I can't make it any simpler. We can't make it any simpler, but what we can do is instead, let's just call this thing on. On of x. Still a function of x. Still depends on x. So this part here, this red underlined part, is going to be on of x from now on. And so, let's write it out one more time. We have y of x is equal to y of a plus y prime of a times x minus a plus dot 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 plus y differentiated n times at a times x minus a to the power of n divided by n factorial plus on of x. On of x. And now, well, because we have it like this, I guess another one more way to write that is y of x is equal to the sum from k equals 0. So this is y of x. Y of x is equal to the sum from k equals 0 to n of y differentiated k times at the point a divided by k factorial times x minus a to the power of k plus on of x, plus on of x. So this is our, well, this is not quite our Taylor series yet, but the first part of it, all the way up to here, is called our nth order Taylor polynomial because it has n terms. Now, what we have to pay attention to is this function here, on of x. Let's take a look what happens to it. Now, so I do have to write it out one more time, unfortunately. On of x is equal to the sum from a to x. Oh, sorry, not the sum, the integral from a to x, integral from a to t1, all the way up to the integral from a to tn of y differentiated m plus 1 times at the number tn plus 1, the variable tn plus 1, dtn plus 1 all the way down to dt1. Okay, what we can observe is that as x gets closer and closer towards a, what's going to happen to this thing? As x gets closer and closer towards a, well, the first integral, we're integrating from a. If the closer x gets to a in that first integral, the smaller it's going to get overall. And in fact, for x equals a, this thing is equal to 0, as we knew. So as x gets closer and closer to a, we can actually say that on of x gets closer and closer to 0. And hence, since y of x minus on of x is equal to the sum from k equals 0 to n of y differentiated k times at the point a divided by k factorial times x minus a to the power of k. Since y of x minus on of x is equal to that thing, then this thing here gets closer and closer to y of x as x gets closer and closer towards a. So I can say this gets closer and closer to y of x as x gets closer and closer to a. So for really, really close x, we can actually use the thing in the box, which is just a polynomial, so it's really handy. We can actually use that thing in the box to approximate the function y of x. Okay, this has been a pretty long video so far, so I think we're going to stop it there. The derivation is kind of almost done. Thanks very much for watching. Make sure you check out the notes and make sure it's all clear to you from there. We'll do more of this in the next part. Thanks very much for watching. Take care. Bye.